The Structural Equivalency Spreadsheet, SES, and Impact Attenuator document, IAD, have been redesigned for 2019. There weren't many structural rules changes, so the requirements haven't changed very much from the previous year's SES and IAD. We've tried to make the requirements obvious, as well as make the workflow easier for students and reviewers. From a frame rules perspective, everything is in one place. This might be a very good place to have experienced students on your team, sit down with new members, and work together. Always have a copy of the rules open at the same time, or if your team is thinking about moving to monocoque construction, definitely read the SES. It'll help define requirements for your design. And from a structural perspective, it does the same thing for EV cars. A big change for this year is the SES has been split into different files. Internal combustion teams with a steel tube frame need to fill out the steel tube SES, plus the IAD, which is due at a later time. EV cars with a steel tube frame need to fill out the steel tube SES, plus an additional HV enclosure SES. That covers the accumulator, attachment, HV protection, and that's due at the same time, plus the IAD, which is due at a later date. If any regulated part of the frame is not steel tube, use the non-ferrous/hybrid/monocoque SES. For EV cars, the HV enclosure file is due at the same time, and the IAD is due later. A note, if the accumulator is composite construction, that's contained entirely within the HV enclosure SES. So an EV car with a steel tube chassis, you use the regular steel tube SES, and the composite accumulator goes into the HV enclosure SES. Take a look at the steel tube SES. The first thing when you open this file up, you're going to want to zoom in. And it's wishful thinking that you'll read everything, but you really have to read everything. The first thing you're going to see is that any cell with a border, that's a free cell. You can put whatever you want into cells with a border. Make your entries. And cells with a thick border, that is going to be a drop-down, and that's only going to let you enter certain values. So you can't put whatever you want in, but it gives you the option, and you have control over those cells. And every category, each tab and the entire sheet, they're color-coded into either dark blue for blank, light blue for rules equivalence, yellow for check, brown for reject, or not applicable. And the status of some cells depends on the entries in other cells. The other very important thing to do when you're first starting your design is to select your units for the entire SES. And the entire file will be done in either millimeters or inches. Leave that on millimeters for now. If we scroll over to the right, there's an acronym list. We use a lot of acronyms in the rules. We use a lot of acronyms in the SES, and hopefully this will make things a little bit clearer. And also, if you keep going, there are a lot of different examples of the front bulkhead support structure, of the side impact structure, and of main hoop brace structure. And there are examples and explanations. If you scroll down, there are kind of 5 guiding principles for each of those sections. All of them have an upper tube, all of them have a lower tube, and all of them are completely triangulated in between the upper and the lower tube across the whole length of the upper and lower. All the tubes have to meet T2.5.4, minimum size, and there should be no quadrilateral openings. Everything has to be done with triangles in between those tubes. The idea behind this is that we'll have a good structure from the front all the way to the back of the car of an upper tube, a lower tube, triangulated in between. And what that's going to do is help there be a good load path in terms of any sort of safety concern, whether it's a front impact, a side impact, and just the general strength of the chassis. There are many examples. If you scroll through all of these, and what they're meant to do is explain how the rules work. I'm sure there are many more examples not shown here that your team can come up with that will meet all of the rules, that will be legal, that will be safe, and you can enter that in the rest of the SES. One note is that any tubes, for example, rear suspension, if it's behind the main hoop brace support, that's free. As long as you don't have any part of the fuel system or the high voltage system in that area, we don't worry about those tubes. And if you do have the high voltage system in that area, that's going to be covered in the HV enclosure sheet. Let's scroll over back to the beginning here. You can see there are even more example images, and they have additional explanations of each portion of the car. Like I said, keep a set of the rules open while you're doing this and read the entire rules. And between this file and the rules, it should make a lot of sense. For each section, what we actually want you to do, once you've read the guidance image, is you're going to take that and you're going to delete it and replace it with your own image that has all of the dimensions that you enter in the section below, so we can kind of see what you're typing into the rest of the sheet. Each requirement in the rules is part of a color-coded checklist. So, for example, here, a steel anti-intrusion plate has to be at least 1.5 millimeters thick, so we put that in. And each requirement feeds into a heading. So if we fill out each of these with something that we know is going to pass, just real quick show, you can see each heading shows rules equivalent. And 2 we know is going to work. Size we know is going to work. And each heading fills into a section. You can look at this entire file from the perspective of what is still blank, what needs an entry, what is filled out, and good to go. And each of those sections will feed into the entire sheet, and each tab feeds into this main sheet. So you can, this is your quick summary of, is this file ready to submit? Is this file likely to be approved? The idea behind the SES is we want as many teams as possible to make it through the frame portion of tech inspection at competition on the first try. Historically, before the SES was required from every single team, you would have half of the teams that showed up at competition. They'd be cutting tubes out, putting new tubes in because they didn't meet the rules, it wasn't in the right place, it wasn't the right size. And now that we require every single team to fill out the SES and we check it before you even show up at competition, it's maybe 3 or 4 out of 200 teams that we see every year in North America that will have to actually make changes to their frame. And everyone else, the frame is already approved. The frame we've already checked. We've made sure that it meets the rules. And that's the idea behind all of these sections. And in each section, there's additional explanation of all of the rules. This part is talking about the requirements to run a front bulkhead with no diagonal. So if your front bulkhead is small enough that the impact attenuator on the front of the car is resting at least on the center line of all of the tubes on the front bulkhead, it doesn't need a diagonal. But if we make that bigger, it says, okay, there are 2 different ways you can do it without a diagonal. Either it's small enough, or it's the impact attenuator is placing the anti-intrusion plate in shear, but you have run a test on it and you've showed that the deflection is less than 25 millimeters. That's fine. If you run a custom impact attenuator, that always has to be tested. So what this tells us, okay, we can approve this, but what we have to do later is we have to check your impact attenuator document. We have to make sure the deflection is less than 25 millimeters. And if it's not, we're going to send the SES back to you and we're going to say, hey, put in a diagonal, and if we put in a size that we know is important, we put it back to standard impact attenuator, that all lights back up. So the sheet is hopefully smart and going to help you see where your initial designs meet the rules and help you modify your designs to meet the rules. And certain parts of the sheet are going to affect certain other parts of the sheet. This is a rule about the angle of the front hoop above the upper side impact. And so if we put that above the 10-degree requirement, we turn it to 11 degrees. You can see over here it turns on a requirement for a rearward front hoop brake. If we take that out, the requirement turns off. If we put in something that exceeds the rule, the requirement turns on. So this will help guide you through certain portions of the design process. Take a look at one of the portions of the car we get the most questions on, and that's the front bulkhead support structure. This is what is supporting a frontal impact from the front bulkhead here all the way back to where the side impact structure takes over. And we took a look at all of the different designs that we saw last year and in previous years, and there are kind of 3 generic configurations that are allowed by the rules. And type A, you have the upper FDHS tube, and that runs from the top of the front bulkhead to the upper side impact tube. You have a lower, and the lower always runs from the bottom of the front bulkhead to the lower side impact tube. The upper has a window. You don't have to make them meet exactly, but the lower does not. And they're completely triangulated. Another option, if you put the upper FBHS tube outside of that window of the upper side impact, you can put in a rearward front hoop brace, and that'll support that front impact load. So the impact load comes in, goes through the FBHS, and is then transferred to the side impact structure, and it takes over back here. The lower still runs from the bottom of the front bulkhead, the lower SIS, and it's completely triangulated in between. A third version that is actually fairly popular with a lot of different teams, the upper FBHS tube is above the upper side impact, and it is braced rearward by a rear front hoop brace. And the lower actually has two different portions. One of them runs from the bottom of the front bulkhead up to that window at the upper SIS tube, and then an additional path from the bottom of the front bulkhead to the lower SIS. And it still has to be completely triangulated in between the upper and the lower, but you have this space where it doesn't have to be triangulated, just like you have a space between the forward front hoop brace and the upper FBHS that doesn't have to be triangulated in Type A. So take a look at your design, determine whether it's Type A, Type B, or Type C, and then you come down, and that'll be one of the entries that you have to make, and that will affect other requirements. If we switch it to Type C, it knows that it needs a rearward front hoop brace, and it turns that requirement on, just like the angle of the front hoop. The next section, the upper side impact structure, that has different requirements depending on whether your upper side impact tube is a single straight line tube or whether there's a bend or it's made from more than one piece. That's going to change the size that you have to put in. We'll do a quick example here. Normally that would be 1.6 millimeter, 25 wall thickness with a 25.4 millimeter diameter. That passes. But if it's a bent or a multi-tube, the size has to go up. That's one of the standard requirements under TE 2.5, so we can see that it has to become, at minimum, you can always put in something that's bigger, a 1.2 millimeter wall thickness by, I believe it is 1.5. No, that's not big enough, so let's put 35 in. Yeah, 35 is the requirement. And it goes from a reject coating on that section to a rules equivalence coating. If you have any section of your car that is coated reject, you almost certainly should not send that into us. It is almost certainly not ready to send in. That's a design change that you need to make before this file is ready to submit, before your chassis can be approved. Another example that we had a lot of issues in tech inspection in 2018 with teams mounting their rear wings to the middle of the main hoop brace. Now, rules T2.13.5 and E2.13.9, those were added a few years ago to ban this. And everyone stopped doing it, but then new students come in and teams started missing this rule. The concern is if the car rolls over and there's a mount from the wing on here, that tube might take a hard hit from the wing hitting the ground first before the roll hoop itself hits the ground. And this main hoop brace, its job is to keep the roll hoop from folding over in a roll over situation. And if it takes a hard hit from that rear wing hitting the ground before the main hoop hits the ground, it might not fail the tube from the rear wing hitting the ground, but in terms of fatigue, it might not be able to survive the next hard hit when the main hoop itself hits the ground. So that's why we want you to keep rear wing mounts. We want you to keep them at the nose. If it's the nose, it's got a good load path, it can transfer the load. We're not worried about it buckling. Or if you've mounted it somewhere else on the car, that's going to be fine, but we are going to crack down on rear wing mounts in the middle of the main hoop brace, and of course the main hoop itself would be equally bad. So that's something that's coded in down here. Have to make a selection as to what design direction you've taken. And in the future, as more issues come up, as rules change, we'll be able to add more checks or remove them from the list from the SES files as you fill this out. Move over to the welded tube insert tab. And this tab, you can see it's got some blanks in it right now, and that will feed back to the main tab, which will read blank until this is filled out. If you've got any holes drilled in any of the tubes that are required by the rules and they're over 4 millimeters, for example, you've got a suspension pickup in there, or you've got some pedal box holes in there, if you have holes that are drilled in there, that's going to turn on this requirement. You'll have to fill that out. It's going to need either an insert or a cap on it. A cap's more likely if you've got the steering rack running through the middle of any tubes. On the other hand, if you don't have any holes, you don't have the steering rack, you just select no for both. Tab lights up as rules equivalents, and you can move on to the next one. This is if you have any removable members, any tubes that are required by the rules, but you can bolt them in and out of the car. If it's yes, it'll turn on the requirements. If it's no, turns on rules equivalents. That'll feed back into the main sheet, and you're good to go. You can kind of see the workflow where you're going to work through the sheet. You're going to fill out the blank tabs that have a blank next to them, and you're going to check your entries. The sheet is going to enforce the minimum tube diameters, the minimum tube thicknesses, all the way through this file. Delete all of these guidance files and replace them with your own tag, and show all of the dimensions that you've entered throughout the different sections. Don't miss these main ones for the overall chassis. And once you've done that, ideally you're going to have rules equivalents, or check, and then your SES is ready to submit, and you should have, if you've done everything correctly, a very good chance of, or certainly an increased chance of being approved on the first submission, which was another goal for revising the SES this year. If any portion of your frame is not steel tube, you're going to need to use the non-ferrous /hybrid/monocoque SES for the majority of your frame. And if we switch over to that, you can already see it's very much the same structure. It's got guidance over to the right. It's got the different sections that need to be filled out. Let's zoom in here. And something that's new under the front bulkhead is material property. So if you're making a welded aluminum frame, or you're making the portions of the frame that may be, according to the rules, made out of aluminum tube, you need to put in the Young's modulus, you need to put in the yield strength, you need to put in the ultimate strength. And that, if any portion of your aluminum frame is welded, those numbers, it must be welded numbers for the entire frame, unless the entire frame is later heat treated and aged. No welding is allowed on any titanium tubes or magnesium tubes, not even suspension tabs, nothing like that. It's too difficult to control in this series, so that's why that would be a situation where you would have a lot of voltage members on your car. And once you've fed in, if you're using any non-steel tubes, once you've fed into those numbers, you can come in and for tube construction on the front bulkhead, you can select that material, and let's just put in some, we've got some dummy numbers in there to show. If you select welded aluminum, it will pull up the Young's modulus and it will pull up the yield strength. And what this is doing is it's looking at whether there's a bigger difference between yield and the steel yield or ultimate and the steel yield. And it'll use that number for the comparison of the buckling modulus, the yield, the bending strength, the deflection, the energy, and make sure that one, the size, the minimum size of the aluminum tube is met, and two, the strength in all of these categories matches the steel baseline. And each different section, just like the steel tube, you have the option to put in tubes other than steel where that's legal. Now, even if you have a aluminum tube car or a full monocoque car, certain portions of the frame need to be specific materials. For example, the front hoop must be metal, and the main hoop must be steel. And as well as the main hoop brace. The main hoop and the main hoop brace must be steel. There is no option to use a different material. And so you'll work through the different sections on your design. The same principles apply for monocoque cars as they do for non-steel tube frames. You're going to go through each section. You're going to select the type of construction that each section of the car has. So, for example, front bulkhead support can be tube or hybrid or composite. And if we turn that on to composite, it's going to turn the requirements off on the tube chassis tab, and it's going to turn the requirements on over here on the composite chassis tab. And a quick note on hybrid cars, if your team's looking to do some simple composite panels, the SES is set up to do equivalent for hybrid equivalents on the front bulkhead support diagonal or the side impact diagonal. So those are two simple panels that you can use the SES to do flat panel equivalents and put into a tube frame. So the rest of the frame would be filled out on tube chassis, and then those sections would light up on the composite chassis file. And because you have told the SES which tubes are there and which have been completely replaced by composite, it knows where to light up the different attachment sections on where a tube is attaching to a composite panel. The SES had to be split into two different categories. This is possibly a little bit tricky, but it's just two different sections, just like the tube frame. It's split into the upper tube, which on a tube frame has different requirements for a straight tube and a bent multi-piece tube, as we saw in the steel tube SES. And so that had to be split out from the lower and the diagonal tube. If you're running tube frame, both of these will be tube. If you're running a hybrid, the only one you'll put on hybrid is lower and diagonal side impact. And if you're running composite, both of them need to be composite, otherwise you're going to get that reject code. So they're composite, and now you're back to rules equivalent, and additional requirements are turned on the composite chassis tab. If you're doing a non-steel tube frame, none of the requirements are going to turn on composite chassis. They're all going to stay turned off, and all the requirements will be on the tube frame. If you're doing an entire monocoque, aside from the front hoop and the main hoop braces, all of those requirements will turn on in composite chassis as well as the attachment. Move over to the T231 composite tab. This is where all of the tests from the old SES have been put onto one tab. So there's the steel tube rig, which is how we establish the test fixture compliance, and that gets fed into every single composite test. You only have to do one, and then that same test gets used for every different three-point test for the different composite panels you do. There's the composite three-point test. There's the perimeter shear test, which is required by certain sections of the car for shear strength for attachment. And last but not least, there is the lap joint test, and this may be required if you have any structural adhesive joint in a composite design. For example, if you are putting a cap over the front hoop inside a monocoque, and both of those things are happening after the main cure. Something that's new for this year, let's zoom in. We're getting a lot more official about the way we ask for detail about what the composite layup is. So the first thing is, are you using an aluminum honeycomb panel, or are you using the usual fiber reinforced composite? So we'll select that, and we want you to put in what is the kind of the core and the specification on the core. What is the resin material if it's fiber reinforced? What is your processing? Are you doing pre-preg, wet layup, some sort of resin infusion, something else? Let us know. It's very useful to know the techniques that the teams are using so we can tailor these documents to make sure that they are going to meet rules equivalent. What sort of cure are you using? What sort of temperatures, time? The other thing we're looking for is actual layup schedules. We've always asked for this, but we've had a lot of uncertainty as to where to enter that, and a lot of uncertainty as to what sort of format we're looking for. So in this box here, just type your layout out for us so we can see what you're doing, and that's really going to help us understand what we're looking at when we're looking at the different tests. And that's also going to help us determine whether additional tests are needed, whether it meets the definition of quasi-isotropic or not, which is entered in down here. But we'll get back to that in 1 second. The basic quasi-isotropic layup is 0, plus 45, 90, minus 45. And you can play with the order of that a little bit, but you need all of those fly directions in order to make sure that it is actually going to have the same material properties in all directions. And you need the 0 and the 90 and the plus 45 and the minus 45 to account for any asymmetry in the fabric itself. Even plain woven fabric has subtle asymmetries between 0 and 90 and plus 45 and minus 45, so we want to account for that. And of course, if you're using a lot of unidirectional, that's wildly asymmetric, so you need to balance it out. If your layup is not quasi-isotropic, that's fine. There's no problem with that at all. You can run any layup you want, but you're going to have to run an additional test, and this has always been in the rules. It's something that we are taking a closer look at. You're going to have to run an additional 3-point test. You're going to have to run it with the layup at 0 degrees, as it is on the car, and then you're going to have to make another test panel that the layup is turned 90 degrees and it's the same size. You have to run the test twice, and that needs to be, according to the rules, at least 50% as strong as the main direction. And filling out this table will help you determine whether it meets the quasi-isotropic rules or not. So let's just put in an example. You need to put in each different kind of fly that is used in this table. Let's put unidirectional. And we would want the weight, and we would want the material type in there too. This is just, we'll do this properly. Unidirectional, and let's say, I don't know, 300 grams. And what this is going to do is it's going to count up the number of flies in each direction, and it's going to come up with a total. So if we go 1, 0, 190, 1 plus 45, 1 minus 45, the bias is 0. And it meets rules equivalence. And you can see in your results here that the layup is quasi-isotropic. You only have to test it in one direction. You can score the core thickness up and down, and that's true of any layup. You can always score the core thickness up and down, and you can also do as many multiples of the test skin as you want. So you can take that, you can double it, you can triple it, quadruple it, whatever you need to do. One detail, when you're scaling the core up and down, it has to be the same material grade. If it's a honeycomb, it has to be the same wall thickness, it has to be the same cell size. If you just use one type of fly in your layup, you're done. If you've used multiple types of flies, let's say you've done a carbon fiber, spread toe, 175 grams. It has jumped into another cell. We're going to come back here, and we're going to say you have 2 at 0, 2 at 90, 2 at plus 45, and 1 at minus 45, and 0 at some other orientation. And now the layup has a bias of 1. So it has counted that, and it can see that that minus 45 is unbalanced by 1. And that's fine. It's still quasi-isotropic. You can have a bias of up to 2 in each skin, and you don't have to do that second test. However, if you take this skin and you double it, now you're at a bias of 2. You have 2 unbalanced flies, and therefore you can't scale it anymore. So it tells you, okay, the core can be scaled up and down, and you can double the skin, but no more than that. So that's something over on the composite chassis that we'll get into. So you can kind of see how this works. And this is the one tab that is not tied back into the main tab. The T2.3.1 composite tab is the only one that does not affect whether this is blank or rules equivalent or check. What that allows you to do, if you mess up and you delete this tab, it's not going to break the sheet. If you delete any of these other tabs, it will break the sheet, so don't do that. But you can make as many copies of this tab as you want. Create a copy. And that has done it over here. We'll move it here. Now you have composite and composite 2. You can rename these tabs whatever you want, and that'll help you keep track of what's going on. That's also going to help us keep track of what's going on. Let's zoom in to the composite chassis tab. This is your material properties table. It's very much like the material properties for the aluminum and the titanium and the magnesium tubes. And we want you to enter the name of the tab. So this one is named T2.31 composite. Rename it whatever you want. You could name this one T2.3.1 composite, but we want it to be composite 2. We want the material name to match the name of the tab here. And then you need to take this, these cells are automatically linked to the original T2.31 composite tab. But you can delete that. It's not a big deal. You can put whatever you want in these cells. These are bordered cells, so you can do whatever you want. And you will, especially if you're doing multiple composites, you will have to manually enter the Young's modulus, and that has to be done in pascals. The ultimate strength must be done in pascals. The shear must be done in pascals, and the inner and outer skin thickness plus your scaling limit. So that all has to be done manually, and that means that we have to check all of that manually against the tab and the results here as well. But these properties will feed down into all of these sections so that you can calculate all of those equivalents, the bending, the deflection, the energy, the offset, as applicable for the different sections of the car. You have a lot of flexibility on this tab. You can name them whatever you want, and you will have to manually enter in these values to match these tabs here. While we're talking about naming, let's switch over to the material documents. We need material properties. We need receipts or shipping invoices or letters of donation. We need that for any non-steel tubes. We need that for supplies you're using, for the resin you're using, for the core you're using. You can't give us too much information here. So we really are looking for some very good knowledge on, some very good documentation on these are the exact materials we use, and it's going to match into all of the tables that you filled out on the different composite tabs or the different tube chassis tabs. So definitely don't miss this tab. Last but not least, I think we've covered everything in the composite chassis except for you've got another nice, this is a summary of the entire car. So you can take a quick look at this and it'll tell you what material has been entered. It will tell you whether you need to make another entry or whether you've met equivalence. It's also going to tell us the core thickness. It's going to tell us the outer skin thickness and the inner skin thickness. You can't change these values, but they're driven by all of the other values throughout the tab. And that's going to be really nice because we're going to be able to scroll over here and you're going to give us a very nice different view, front 3/4, rear 3/4, and additional images to take a quick look at the chassis and have a really good understanding really quickly of how everything works. Monocoque teams will need to, as with all of the other sections, take these guidance images, delete them, and replace them with their own CAD. It needs to show the cross-section being used for equivalence. It needs to show the outer skin thickness, the inner skin thickness, the core thickness, as well as the second moment that is going to be used for bending equivalence. Now that can be a second little image that's patched in. We understand you've got some flexibility there. And as we come down here, very similar to last year's SES. All of the entries are the same in terms of panel height. We'll put some dummy values in here. Core thickness, outer skin thickness, inner skin thickness. The new thing is that we're always asking for this cross-section, the half width of that chassis, and then we're always asking for that second moment to be entered in rather than starting off from a flat panel assumption. The only portions of the car that will always be calculated as a flat panel are the vertical wall of the side impact and the horizontal floor of the side impact. So those sections are slightly different. They don't have these D and IZZ entries. They're not required because that's not how the calculation is done. But for every other one of these, we'll put in some dummy values, and your second moment is going to be some very, very large number. That's throwing an error because I've forgotten to put an equal sign in there. We'll put equals because I've done a calculation, and now it's happy with that. And as we scroll down, all of the equivalent looks really strong. You know, everything looks really, really good here. Massive buckling modulus, ultimate strength, bending, almost no deflection, and that's because I put in some enormous values that are equal to steel for the composite tab. So your numbers will not be this high. Now, if you want to do a flat panel calculation, if you want to just use the vertical wall instead of the entire cross-section, that's absolutely fine. There's no problem with that. What you need to do in that case, you need to put in 0 for D, and you need to set this equal IC1, which is the outer skin, to IC2, which is the inner skin. Now we plug that in, we've got it as strong as steel, and we've got all these rejections down here. You've got to watch your units on this one. These calculations, as with the previous SES, are done in terms of meters raised to the 4th power, whereas this entry is in terms of millimeters raised to the 4th power. So we need to take that whole thing. We need to make sure our units are correct, so we need to multiply it times 10 raised to the 3rd, or millimeters to meters, times 4, 4th power, and then we're back to having something that's very strong, that has a very good equivalence, and that's a process that you'll need to follow for each different section under monocoque equivalence. It will return a value of check if you're between 95 and 100% of equivalency, or between 100 and 105% of deflection. That's acceptable. You can submit that, but we're going to look very, very closely and make sure that the rest of the design is good, the rest of the design makes sense, and that there isn't something very simple that could be done to get everything to 100% equivalent. One last note is that these images are different for the front hoop mounts, the main hoop mounts, and the hoop brace mounts, but the requirements are the same underneath. The tests are the same in terms of backing plates, inserts inside, tear out and pull out. One thing we get into a lot of discussions of is free edge or tear out, and that's where these two fasteners would tear all the way to the bottom, straight lines, until they popped out the bottom of this composite. And the definition of free edge is where either the composite stops, like it does right here, or if, for example, this was a side impact and the floor went off here and you had this corner, it would come out the corner. It would not turn around the corner and keep going around the floor. So that's going to be your free edge distance. It's to either the nearest end of the composite or to where the monocoque structure turns a corner. Every team filling out the non-ferrous hybrid monocoque SES needs to fill out the T2.41 harness mount tab. And it might be very simple. You know, if everything links, if every harness is attached to a tab on a steel tube, select all of those drop downs, but it's on a steel tube, and then you can see the only thing that lit up is we need to know the spacing between the shoulder harnesses to make sure it meets rule T.4.5.4, so let's put in 200. Rules equivalent, entire sheet is equivalent, that is fed back to the main tube chassis sheet, and you're good to go. If you're running non-steel tubes, the harnesses still need to be attached to a steel tab, so that will have to be bolted onto those tubes, so you can tell a steel tube on the drop down here. And if you have attached your belts to the monocoque, that's going to turn on additional requirements. That's going to turn on requirements for lap belt attachment, anti-submarine attachments, 5th, 6th, 7th point attachments. We can turn that down to 5 points, and you can see this turns back off. If you have 6 points, it'll be covered by the anti-submarine and lap belt, but that's there to make sure it's strong enough if you are running a 7-point harness. And what you're going to need to enter in is the dimension of the test panel for the shoulder harness, and that cannot be bigger than the actual cross-section that's taken out of the car. So it can't be wider or it can't be longer than that panel. And then it also needs a minimum distance to the fixture, and that's common to all of these tests. And that also means that if the lap belt and the anti-submarine belt are sharing an attachment, if both of those belts are hooked into the same hook, the requirements goes from 13 on the lap belt and 6.5 on the anti-submarine belt, and those are added together, and both of them have to be 19.5, and you need to put that in for both of them. If they don't share an attachment point, then it needs to be 13 and 6.5. And those attachment points, if they're not sharing, they need to be further away than the points in the test fixture. Otherwise, it's like they're sharing the same mount. If it's 2 different hooks and they're in the same insert, or if it's 2 different hooks and 2 inserts and they're closer together than the test piece, they might as well be part of the same attachment. So we would want you to select yes for that, and we would want you to hit 19.5 kilonewtons for that, spread over those 2 hooks. So that's the end of the harness mount. That is the end of the non-ferrous hybrid monocoque section. Let's go to the HD enclosure, and this is specific to ED cars. So every ED team, whether you're steel tube or whether you're monocoque, you will need to fill out this form. And again, looks very familiar in terms of layouts to the previous forms, a lot of similar tabs, material documents still very important, T2.3.1 composite test tab, and that can be used both for the accumulator container, if that is composite, as well as for the chassis structure that it's being attached to, if that is composite. You have the bolted members, which we've seen before, the welded inserts, which we've seen before, both of those in both the previous SESs. And the main tabs that are different here, there's the HD protection tab, and there's the attachment tab for the accumulator. So let's zoom in, scroll over, and there's a very similar material properties tab that should be familiar from the monocoque SES that we just looked through. You can call these materials whatever you want. You have to enter the different properties and tell us about the scaling and the skin thickness, and that will propagate down into all of the different sections. The accumulator has to be protected up to a height of 350 millimeters, and it's very much the same requirements as any other tube frame or any other monocoque. For tube frame, it's upper, it's lower with a diagonal in between. For monocoque, it is the strength of those same 3 tubes. And so your instruction selection construction, whether it's tube or hybrid or composite, and whether and the material that is used. This is where you would enter it if it's done for a tube, and this is where you would enter it if it's built with a composite. You get to select your different materials down through here. And then you will enter the properties of the materials, and that will tell you whether you have equivalence or not. Same thing for tractor side protection. There's a smaller tube requirement, upper, lower diagonal, just the tube size isn't as big, so the requirement isn't as high. For rear impact, this is something we're clarifying for this year. We're not going to require you to triangulate entirely across the rear, but we really need any part of the high voltage system to be protected in a rear impact, and that means either the entire thing, the entire drive line is completely enclosed, or, for example, if you have the differential behind the rear tubes, then there will be at least 2 tubes that will stop that differential from pushing through into those high voltage components. So there cannot be clearance for either a 10-inch diameter impactor or for any other non-crushable part of the car that is behind the rear impact. That cannot be pushed through. That has to be prevented from being pushed through in the rear impact. And you're welcome to use the differential mount as part of your equivalent. You can put in the material properties at the top, and you can feed that down through the properties that will give you equivalence here. We are going to be asking for a lot of information to help us with the structural rules in the future about the way the accumulator segments are built. We're going to want to know about the cell type. We're going to want to help you meet some of the basic electrical requirement rules just to get a sense of how much mass is how much capacity and how much power in terms of these accumulators. That's a good thing for us to know when we're looking at how much does the entire system weigh. And what we're really interested in this year is the strength of the material being used to actually hold the cells inside each of the segments inside the accumulator, because that's where most of the structure for the accumulator is coming from. It's coming from that internal structure holding the cells inside the segments. And that is what a lot of our new accumulator mounting rules are based on. So we do not, at this time, have specific requirements for that. This is an information gathering section that's going to help us develop requirements for the future. And we're also looking for how are those segments installed inside the accumulator when you place them inside the box. The container itself has some specific rules that need to be met, and that's going to be determined by the segment mass, that's going to be determined by the number of segments, and that is going to drive the number of fasteners. And you can look at the way the walls are attached, and that can be bolted or welded or bonded, depending on your construction. It'll have to meet the equivalence. You will need if we switch this over to bonded equivalence, it's going to ask for the shear strength of the number of fasteners you would otherwise use. And so that's going to be another material document that has to be provided. It's going to ask for the shear strength of the adhesive and the minimum bond area. Those are material documents that you need to provide. And that'll calculate whether the bond is equivalent to the number of bolts that would otherwise be used. And the floor and the exterior walls and the interior walls, those equivalences will be calculated for a composite construction box from the material properties that are entered that are based on the T2.31 composite, and that'll be calculated for composites, or if you simply enter steel and 1.25 millimeters, that goes to equivalent, and as soon as you tell us the dimensions, that section is good to go. So it's more complicated if you're using composite, but it's still all in the same place. It's still all of the same techniques that were used through the monocoque and hybrid sections of the SES. Let's move on to accumulator attachment, which has been a big point of contention over the past few years for all EV teams. This has been one of the more difficult requirements, so we've tried to make this a lot more clear in terms of our expectations. And we have also introduced a new option with the corner attachment rule this year, which we should actually go back and talk about. As mentioned before, the majority of the structure of the actual accumulator is coming from the interior segments. So those interior segments are going to define what the corners of the accumulator are. If this has an extra section on top for more electronics, we're not worried about that. That's not where most of the mass of the accumulator that we're worried about is going to be. It is the accumulator segments. They're going to have most of the mass and most of the structure. And you can make that structure bigger by adding a perimeter of tubes, one tube thick. That can help you stretch it out so that it can meet your pickup point. Or if you're doing a composite accumulator, you can increase the core thickness, both in your interior walls and your exterior walls. And that'll help you tailor your accumulator size to the rest of your chassis and to meet your pickup point. So we asked for the total mass of all segments and the total accumulator mass, which we know is different from the mass of the box itself and additional electronics in there. And that'll tell you if you decide to go with the 8-corner attachment, which is 4 on top and 4 on the bottom, this is the test load that each mount will have to meet. If you are not going to use corner attachment and you're not going to restrict those attachment points to those specific locations, the load goes up to 15,000 newtons, and there's a minimum number depending on whether it is a certain size or not. So if we turn this up to 40, that's going to go from 8 to 10, so that's 39. The next thing it asks is which mounting method you want. Are you going to go with corner attachment or mass-based? We'll go with corner attachment. And then it asks you, almost certainly you're going to want to design this so that all of the mounts are the same from the left to the right, or all of them are the same from the front to the rear, or all of them are the same from the top to the bottom. And so it asks you about the accumulator side. Are they all the same on any of those options? And also on the chassis side, because you might have different kinds of symmetry on the accumulator versus on the chassis. And what those will actually do is, if I can get this on the screen here, there we go. If it's front rear, it tells you which accumulator mount it's talking about. And if we change the top bottom, you can see the names change. So this will help you keep track of what's going on with your accumulator mounts and with your chassis mounts. If we scroll over to the chassis mounts, these names will also change depending on the symmetry you select. If your mounts are asymmetric, if you have more than 5 different kinds of accumulator mounts, more than 5 different kinds of chassis mounts, all you need to do is make a copy of this tab and then just fill out the math in exactly the same way with all the different requirements. And that'll allow us to take a look. But hopefully this will keep things fairly simple. With the mounts themselves, you can imagine many different ways that the accumulator is going to meet the chassis. Maybe the accumulator goes directly to a welded insert in the chassis. That's going to be a direct mount. Maybe there's a mount on the accumulator, kind of a tab here. Maybe a mount on a tube frame, there's also a tab here. And maybe you have a mount on the accumulator that goes to a mount on a structural composite. If you're using the corner attachment rules, again, the segment structures are what define where the corners are. If the accumulator box extends beyond that, we're not concerned about that. And so what we're interested in is where are the mounts relative to that corner of that accumulator structure. And if you come down into each mount, it's going to ask for, is it inside or outside the front and rear surfaces? Is it inside or outside the top and bottom surfaces? Is it inside or outside the left and right surfaces? If it's inside all those surfaces, if it's a direct mount like this, it's going to be inside, and then there is the 50 millimeter limit. Would you put in 50, 50, and 50? And the sheet is going to know that you don't need to add a tab for that. It's going to know that it's built directly in, and so the only thing we're going to worry about is the strength of that insert that's inside the accumulator and making sure that's not going to pull out or tear out. If one of those is outside, it's going to turn on the need for some gussets, some braces on the tab that must be sticking out that certain distance. The one exception to this, we scroll over, if you have less than 12.7 millimeters, half an inch of offset, we're not going to require you to put gussets or braces on that. We put this in here. And we turn them all down to 12.7. That's going to turn off the requirements for the braces. So we need you to define thinking about where is the mount relative to that corner. And this guidance tab goes into a little bit more explanation. Again, take all of these and delete them, and show us what each of your mounts looks like with the dimensions that are required in all of these sections down below. So here's the inside structure of the segment. There's a 50 millimeter limit looking at it, and whether this is from the top or the side or the front, this is the restriction that you have. So you can kind of go 50 millimeters along the 3 different axes. And the one detail, we're not going to count your skin thickness. So if you have a sheet metal skin, that thickness does not count towards that 50 millimeter limit. If you have a big, thick composite skin with some core in there for some good structure, we're not going to count that towards your thickness limit either. The other detail is, again, if you have a volume above the segment structure, that is still considered outside the segment structure, and then there's no skin, so the 50 millimeter limit starts right at the limit of the segment structure. When we're talking about the mounts themselves, the bracelet has a length that is resting on the accumulator itself. So the tab or the brace for the tab has a length, and it doesn't matter where that is relative to the pickup. The map is going to turn out the same. If you're less than 12.7 millimeters, you don't need any gussets on that. You can just have a tab sticking right out of that accumulator. And we also want you to respect that 12.7 millimeter limit if you have a tab that the gusset starts beneath it. We prefer that your braces and gussets run all the way to the top of the tabs that you're using for mounting, or at least to the center line would be good. If you're using a tube, stick to that same 12.7 millimeter limit and make sure you put a welded insert in there to prevent the tube from being crushed if that's the way that you want to build your mounts. There are a lot of different ways you can imagine building your mounts and running your gussets to make sure that they are transferring the load from this mount, and that test load is going to be determined back where you enter the mass of the total accumulator, and making sure that they have good load transfer back to the internal accumulator structure. And if it's sticking up above you and through a volume, you need to make sure that there's additional bracing or gusseting inside to get that length that's needed, to make sure that it's not going to fail in bending, to make sure that there's enough weld length on it or there's enough bond area on it if you're bonding it. You can use any number of different shapes. You can add up angles like this to get the required length. You can add up angles like this to get the required length, but you have to think about these in terms of the 3 main orthogonal directions. So lateral, longitudinal, and vertical. That's how your requirements are going to be determined for the lengths that are needed for each different brace. You are welcome to use one fastener for 2 different mounts. There just needs to be a 50 millimeter minimum spacing in between. If you have a really skinny pack, you can use this technique, and this will be entered as one of the mounts, and this will be entered as one of the mounts. And in both of those places, the fastener will be in single shear, and it will have to carry that same load through all of these tabs. We really want you with a tube frame chassis, we want you to have your accumulator mount for good load transfer close to a node on the chassis. And so when you have a node of 3 tubes coming together, and it needs to be at least 3 tubes, we want to make sure that the pickup is within 50 millimeters along the axis of one of those 3 tubes, and within 50 millimeters of the surface of that tube, kind of an offset that gives you something that is, the tube's going to be usually about 25 millimeters with a 50 millimeter offset. That's going to mean you have about a 125 millimeter diameter cylinder to locate that mount in. If you're mounting it to a composite car, a monocoque or a hybrid panel, we want you to stay within 50 millimeters of that surface for the mounts that you're building on the composite side, just like we want you to stay within 50 millimeters on the accumulator side. That's so that the mounts don't get too big, the moments don't get too big, and there's not too much of a moment that needs to be reacted in terms of the test load. If you are doing tube mounting to a tube chassis, you can use just 1 tube, and you can run that with a gusset back to the tube chassis. Ideally, you'll be able to run a couple of tubes or a brace that runs to multiple tubes so that you can brace it in multiple directions. But we understand you need to get the accumulator in and out. You need to have tubes in certain places based on other rules and for other design constraints. So we've tried to give you as much flexibility as possible. Another thing that hasn't been mentioned yet is the idea of having a subframe. And if you wanted to run a subframe directly to a mount on a monocoque or a hybrid car, and then build it with some nodes that'll meet this same requirement on as if it were a two-frame car, and then run your pickups to there, that'll be completely fine. Make a copy of this attachment tab and repeat all of the math to make sure that all of those places where the subframe attaches to the monocoque or the hybrid are just as strong. Additionally, if you want to run a subframe to a two-frame car, you just can't quite get the tubes in the right place and you have to add a couple of extra tubes to get the nodes in the right place, run the same math, make sure all of your attachments are strong enough to meet the test load. And when we say subframe, what we mean is tubes that run from ideally one side of the car to the other, or from one end of the accumulator to the other, as opposed to a bracket on top of a bracket on top of a bracket. If you're going to do a subframe, run it all the way along that side of the accumulator when you build it. And that will help you have good load paths, a good structure, and keep the number of attachments to a minimum. The last point we need to make about the HV enclosure FES is that previously most teams have jumped right to FEA for analysis of the strength of their mount. This year, even if you're doing the math-based and you're not doing the corner attachment, all of the same math applies to the design of your tabs and the bracing for those tabs and the attachment back to the chassis. All of the same math applies to make sure that your mount design is going to be strong enough. And so you should be able to do the math for a 15,000 Newton mount in these same sections that are used for each different accumulator mount and for each different chassis mount. So we hope that that's another thing that will make the SES process much easier and more clear and lead to some better and stronger designs for teams this year. And that wraps up the EV-specific SES. So let's move quickly to the impact attenuator document. Again, format is very similar to things that have happened before. Every single team needs to fill out an impact attenuator document. Even if you're a two-frame, even if you're using a standard purchased impact attenuator, you still need to come in. You need to tell us what kind of impact attenuator you have, what the material is, the description, the size, what your AI plate is, and whether you have bonded it, which is a requirement. You must use glue going forward and not just bolts for the standard accumulator. And if you are using a custom accumulator, that is going to turn on all of the additional requirements for the additional tests. And we'd really like to see an adhesive calculation, even if you're running a standard accumulator. And if you say no, that's going to tell you to reject it. If you say yes, you come over here and it's going to ask you to enter the value and make sure that the shear strength of the adhesive being used, which needs to be specific to both the polystyrene of a standard accumulator and the steel or aluminum or composite of your anti-intrusion plate. It needs to be suitable for both, and you need to pick the lowest value to make sure you have the equivalent to those 4 fasteners that would be used for a different kind of impact attenuator. You need to tell us whether you have a front wing, either no front wing or it was physically tested, or a calculation to make sure that the attachments or the mounts are going to fail before you cross over that 120 kilonewton rule limit. And if you're running a custom attenuator, you need to run a dynamic or quasi-static test, and the data for that needs to be entered into here. And you can also do your energy calculation in this column. We need pictures of all of these things. We need the results of all of these things, and we need the energy calculation. And just like the other sheets, it's going to run a lot of different checks to make sure you're in compliance. And the last one that's fairly uncommon, if you're running a structural carbon shell, kind of a nose cone as your impact attenuator, that needs to go through a peak force test to make sure that the anti-intrusion plate will hold 120 kilonewtons. So when you test that thin wall carbon nose cone, it needs to not only be crushed for energy compliance and deceleration, but you also need to make sure that it's going to hold up with the anti-intrusion plate to that peak force. So that'll be a second test with log data. Final note, with monocoque cars that are running a custom attenuator, you're required to do a test for any custom attenuator, and you need to make a replica of the first 2 inches of your monocoque out of the same carbon and core construction that are used on your car. We are no longer accepting steel tube equivalents of carbon monocoques for anti-intrusion testing. And that covers the basics of the impact attenuator document. We've left you plenty of space here to put in your own calculations that are necessary for front wing or any other tests that come up. So you can put any additional comments, calculations, things like that to cover your anti-intrusion